In Calculus BC, we have our vectors day 2 lesson. It's a shorter lesson than our first. So let's look at the top page here. Recall that when a particle moves along a line with velocity v of t, the displacement, which is also known as the change in position, it's also known as the net distance, but regardless of which of those three terms you use, that displacement from t equals a to t equals b is always represented by the integral from a to b of v of t dt. If you'd like to compare that change in position with the distance traveled, also known as the total distance traveled, way back last semester, we would integrate the absolute value of v of t dt. So very big ideas here. Thank goodness the same basic concepts are going to apply as we are working with vectors. So when a particle moves with velocity vector v of t, a displacement and distance traveled can be found by applying the same integrals to the vector v. So we can look right here, this definition. Suppose a particle moves along the path in a plane so that its velocity at any time t is written in component form, v1 of t, v2 of t for our x and y components. The displacement, the change in position in other words, very nicely is going to be a vector, it's given by the vector here, of the integral from a to b of v1 of t dt, integrate the x component, comma, integrate the y component, a to b of v of 2 of t dt. So this is your change in position vector. The preceding vector then would be added to the position to get your final position. So you add what you started with the change. So we were writing that a lot in the past. We'd say write where you start, the vector that you start with, plus the change that you have, and that sum is always going to be your position at time b. Well, distance traveled is actually a little bit different here. The distance traveled we saw in the beginning of our course was actually tied to integrating the absolute value of v. And that's certainly going to be the case right here. But notice that the absolute value of a vector was always the magnitude of that vector. It was the Pythagorean theorem applied to the components. And that's honestly what we're going to do when we want to find distance traveled. So very nicely, we've got a lot of strong parallels to what we were doing in the past. So without any further ado, let's just take a look at example 1. It says a particle moves in the plane with this velocity vector. And at t equals 0, the particle is at the point 1, 5. So for part A, we'd like to find the position at t equals 4. Well, we'd like to find the change in position first. Now, as we're working out the change in position, this is for part A, we realize that we're going to integrate. Our beginning time was t equals 0. The time that we're interested at finding out where our final position is at 4, so we're going to go up to 4. And we're going to integrate our x component. So we've got t minus 3 pi cosine of pi t dt, comma, and then we're going to integrate with the same limits, 0 to 4, put in our y component, 2t minus pi sine of pi t, and then we'll say dt. And realize our final answer is going to be a vector. Well, let's get the calculator out real quickly and see what's going on here. We can hit Math 9, get an integral up, go from 0 to 4. And inside here, we can even type this out as x's, x minus 3 pi, so we'll go second pi over here, cosine of pi t, or pi x in this case. I'll close the parentheses there. And this other parenthesis is indicating it's the close of the integrand. And we'll just say do this with respect to x. Hit enter and you can see we get 8. So right here we'd have 8 for our x component. Let's see what happens when we want to pull up y and integrate with respect to that y component. We'll have the same bounds, but let me just delete this out real quickly. We'll just type in 2x minus pi, and then we'll say sine of pi t. So we're super close to wrapping this thing up, at least for the displacement. I'm going to close the parentheses for the sine. Of course, we've got another set of parentheses to close the integrand. Hit enter and you get 16. So this is your change in position. This is your displacement. To answer part A, however, we need to take where we are starting plus the change. So you can see very quickly that we're actually going to have a start at 1, 5. And you can even write that in terms of a vector, 1, 5 as so. We'll say the change is going to be 8, 16. Add that up. 1 plus 8 is 9. 5 plus 16 is 21. So this right here is our position at t equals 4. Okay, for part B, we'd like to find the total distance traveled. And once again, this is going to be an integral. So thank goodness what we can do pretty quickly is just go right up here to our formula to find that distance. We're going to say we'd like to integrate between 0 and 4 of the square root, and we're going to use that Pythagorean theorem idea. Take our x component, which is going to be t minus 3 pi cosine of pi t, square that, and then we're going to say plus, and then we'll have 2t minus pi sine of pi t, square that. Don't forget to throw in a little dt there. Should always wrap that up. And let's be honest, this is going to be a much uglier looking integral. But all the same, once we do this, we'll get a positive value that's going to represent our distance. And my goodness, we can do that quickly. Now, what you could do is, if you wanted to, and we could have done this even earlier on, I do this a lot. I've shown you guys in the past, we have t minus 3 pi cosine of pi x. That was for our one component, our x component. The other one was 2x minus pi. And then we can say sine of pi x. And I'm just putting this in here to hold their place. Here's why. It can get a little cumbersome to write all this out. It might be a little bit easier to just say I'm going to integrate between 0 and 4. I'm going to type in a square root. But then I need to have that first expression squared, so I'll go y vars, function y1, and say please square that. I'll say plus vars, y vars, function y2, don't forget to square that as well. This is all with respect to the variable I've been using, which happens to be x. In reality, it would be a t. But hit enter, and it takes a few seconds to work this out. But regardless, it's just a matter of a brief amount of time. You'll find that your distance, still thinking here, of course, has to be positive, and it's 33.533. 33.533. Notice this is not a vector. This is actually a fixed quantity. So real quickly, let's move on down really to our last problem. And we're just going to take a peek at the back, change the directions slightly. Find the position vector in example 1 that's going from 1 comma 5 to 9 comma 21. Now the position vector, of course, is very different. You know, it's like an r of t vector. We write that a lot, and that means we need x of t comma y of t. And of course, right now you might be thinking, how on earth can I do that? Well, thank goodness what you really have, if we scroll back up, the velocity vector is honestly always dx dt and dy dt. So that in and of itself is super, super helpful. I can say dx dt is going to equal t minus 3 pi cosine of pi t. And I could say similarly dy dt is going to be 2t minus pi sine of pi t. So you might wonder, wow, can we somehow get what x of t and y of t would equal? Well, you could certainly integrate. You could even separate variables if you'd like. Not that you have to do that, but just going step by step here. We'll put a little vertical bar here to separate everything. We're just going to do indefinite integrals. Okay, we're going to integrate the left side, integrate the right side. I'll get x of t, and let's take some antiderivatives. Antiderivative of t is t squared over 2. Antiderivative of cosine pi t, we're going to get sine of pi t, but we have to reverse the chain rule. We're going to have to divide by pi. And that's just going to get us a minus 3 sine of pi t. I'm going to say plus constant 1. Now look, you should double check that you're right by taking a quick derivative. Take that derivative for both of those. You will quickly confirm that this is correct. As we do the same thing here, antiderivative of 2t is t squared. Take the antiderivative of sine of pi t, and you'd get negative cosine. So we'll get negative cosine of pi t, but of course we have to divide by pi, so the pi's are going to cancel out. Double check, and in fact when you divide by the negative, forgive me, that minus turns into a plus. That's why I'm saying always double check. I just did that myself. As I'm taking the derivative of t squared, you'll get 2t. Derivative of cosine of pi t, you should get negative sine pi of t. Chain rule says bring out another pi. Well, right now we're pretty close to having our position. But if we're going from 1 comma 5, that means that t equals 0, x equals 1, y equals 5. That's what 1 comma 5 is really saying. So if you go from 1 comma 5, you're implying that's what happens when you let t equal 0. So I'm going to let my x equal 1. I'm going to let my t value actually equal 0. By the way, the sign of 0 we all know is 0. So we're going to be left nicely with c1's equal to 1. Plugging in a 5 for y here and plugging in 0 for our t. Please be careful. I hope you're well aware that the cosine of 0 is not 0, it's 1. And as I subtract a 1, I get c2 equals 4. So what exactly is my x of t? My x of t is t squared over 2 minus 3 sine of pi t plus 1. My y is going to be t squared plus cosine of pi t plus 4. And what about your position vector? Nicely write it in bracket form. T squared over 2 minus 3 sine of pi t plus 1, comma, t squared plus cosine of pi t plus 4. And we're done.